Hello, today we're going to talk about reaction quotients and the equilibrium constant. Okay, so remember that in equilibrium reactions we have reactants and we have products. And we can use what's called an equilibrium constant to relate the amount of products to the amount of reactants. It creates a ratio essentially. So the equilibrium constant is K, uppercase K. That's to distinguish it from rate constant, which is lowercase k. And it's essentially a ratio of the products versus reactants. Now remember, at equilibrium, the rate of the forward is equal to the rate of the reverse. So by the time you reach equilibrium, the amounts of products and reactants stay constant, but they're not necessarily equal to each other. If you have more products, you're going to have a larger value of K because you'll have more on the top of that fraction, and then if you have more reactants, you will have a smaller value of K because you'll have more on the bottom. But no matter what, it indicates there's a ratio of the amounts. Now, we have something called Q, which is the reaction quotient. So Q, the quotient there, is the ratio of products to reactants at any point. It could be at the very beginning of the reaction. It could be the middle of the reaction. It could be once the reaction has reached equilibrium. Any time you're measuring the products and reactants and plugging it in, it's called Q, the reaction quotient. But if you have K, K is the ratio of products to reactants at equilibrium. So if Q is equal to K, we know that the reaction is at equilibrium. So just make sure that you're distinguishing between those. So if you have more complicated reactions, you're going to have a more complicated equilibrium constant or reaction quotient. So in order to figure that out, we need to use what's called an equilibrium expression or a reaction quotient expression. It's the expression there, and it depends on whether you're doing concentrations, which should be in molarity, or if you have pressures, which will be in ATM. Now, concentrations, that's why you see QC or KC. Again, molarities, and you'll need to use brackets in your expression. Brackets always indicate molarity. And then pressures, you'll see QP or KP, and you want to use the partial pressure notation there. So when I write PC, that means the pressure of substance C, the partial pressure of substance C. And we'll put that in parentheses. We don't use brackets because brackets indicate molarity. Now, once you kind of figure out whether you're doing concentration or pressure, then you're going to follow this kind of pattern here. If there's a coefficient in your balanced equation, the coefficient becomes the exponent. All right, coefficients become exponents, and it's always products over reactants. One more little rule is that you never include solid substances or liquid substances. They do not affect the value of your equilibrium constant or your value of the reaction quotient. They're still there and they're still necessary for the reaction to happen. So you have to have like some of it present, but the specific amount of it does not affect the position of equilibrium. So the best way to kind of learn this is to just practice it. So I have two examples here. This one we have, they're all aqueous, so I'm going to use definitely KC and C for concentration. You will always put the products on the top and the reactants on the bottom, and make sure that you include any charges. So we have a copper plus 1 ion, and the 2 becomes an exponent, and then we have our lead 4 plus ions. And on the reactant side, I have my copper 2 plus ions, and that coefficient becomes an exponent. And then I also have my lead 2 plus ions. So products over reactants. And that is my equilibrium expression. Now if I change it to QC, now it's my reaction quotient expression. But for the most part, you're going to just be asked to write the equilibrium expression. Another example for this one, let's go ahead and do KP because they're all gases, so we can measure their pressures. And again, you're going to do products over reactants. But this time I want to use the partial pressure notation. So I will do the pressure of NH3, and the coefficient becomes an exponent. And then on the bottom of my reactants, I have the pressure of N2 times the pressure of H2 cubed. And so that is my equilibrium expression for that reaction in terms of their pressures. Here's another example. This time we have gases again. But just because it's gases doesn't mean it has to be a Kp. So let's go ahead and write a Kc for this one. You can measure the concentration of gases just like you can with aqueous systems. You just do the moles per liter, and volume of gases is important in liters, so you can find a concentration. So again, products over reactants, we're going to do the CO2 cubed times the H2O to the fourth, and over the reactants, so the C3H8 times the O2 to the fifth. So that is my equilibrium expression for that reaction. Last example, the decomposition of solid calcium carbonate produces solid calcium oxide and carbon dioxide gas. So we need to write and balance the equation first. CaCO3 solid produces, and these are equilibrium, they're always equilibrium for this unit. So you want to use a double arrow. But it produces solid calcium oxide and carbon dioxide gas. So now we need to make sure that it's balanced, which it is. We've got 3 oxygens on both sides, and the calciums and carbons balanced as well. So now we can write our reaction quotient. So this time we want to write a Q, because it's specific here. It doesn't tell us whether we want to do pressure or concentration. I'm going to go ahead and do QP pressure, because the last one we did Kc, just to mix it up. But remember, we do not include solids or liquids. So we do not include the calcium oxide or the calcium carbonate because those are solids. They're still there. They still need to be there for that reaction to happen, but their amounts do not affect the value of the reaction quotient or the equilibrium constant. So the only thing that we're going to wind up including is the CO2. So for QP, it winds up just being the pressure of CO2, and there's no coefficient, and you have nothing on the denominator. And that's okay. So our QP expression is just the pressure of CO2, and that's it.